So we are Team 6, and what we're going to talk about is secure data aggregation for healthcare, because everyone loves healthcare today. We're all going to learn more about it. So what we are going to talk about is the issue of bias and fairness in diagnosis and admission rates to hospital. So I'm sure everyone has seen these kinds of articles online about the bias within especially gender and race. But we're going to look at a variety of different protected characteristics. So the problem we are trying to address, we want to tackle problems in the healthcare ecosystem that are hard to address, expensive, and often ignored. So for example, the questions you might want to address are industry-wide statistics, such as how full are hospitals. We might want to uncover unfair practices, such as a lack of admission of patients for a certain class without constant surveillance. So we don't have to want to be constantly looking at what's going on. We want to decide, say, for example, answer the question, is the doctor's decision to not admit this woman to the emergency room out of the ordinary? And on a larger scale, we can potentially identify at-risk populations and emerging epidemics. If we can consider data at such a scale, then we will be able to identify outliers and things which would not take place were we just considering the data from one particular hospital. And this might also enable us to uncover underlying causes for certain symptoms which are very common and therefore might get lost on a smaller scale, or for chronic illnesses which maybe don't occur very frequently. So this shows all of the hospitals in the US. So this is an awful lot of data to be thinking about. So if you think about the data from across all of this, in our model, just for the time being, we're going to think about a smaller situation. So let's say we have 5 different hospitals, but we want to share data between them. But they, obviously, because we're in the US, hospitals have some personal interests. They don't want to just be putting their data out there. So rather, we want some way in which the data can somehow be pooled centrally, and we can do computations on it. Now, we've learned so much about homomorphic encryption. This sounds like a great way to do it. So perhaps this is a solution as to how we can somehow have all the hospitals put their data together, do some computation, work out some statistics, and then we can send back to the hospitals so they can benefit from the results from which we are drawing.
So as you can see, we're very ambitious about the computation we're going to do. And you have seen in other private healthcare applications, it sounds as if we really need a pre-trained model and some complicated approximations. And I'm here to convince you that this is actually incredibly simple, very fast, and very scalable. So here we have the raw data on the left, and it comes with different fields, which may include these traits. And the assumptions we're making is that doctors are the ones crafting the fields of these data. So that means when the doctor makes the decision to admit the patients, then the record indicates all the traits that the doctor themselves had looked at and decided that was sufficient. And this helps us in the causal discovery phase when we want to control for the confounders. And here, these features and disease are being put in this tabular form, and you can think of it as just manipulating tables. And they're very simple, very linear. And in the result, we get insights, which are aggregated statistics. I'll do a walkthrough here. Oh, actually, it's not here.
Yeah, like we're going to talk about it.
Okay. I guess I'll do a walkthrough later.
Yeah, so we're going to consider a small setting with only 5 hospitals, and we're going to walk through exactly how we plan to aggregate all of this data. So we're going to make use of a n out of n threshold homomorphic encryption scheme that is very easily built from what's already in SEAL. The benefit of this is that it just requires a very simple extension to the key generation protocols. And once these keys are generated correctly, the data can be treated as if there's only one data owner. So the full power of the seal library can then be used on this pooled data set. So this protocol begins with each hospital generating their own public-private key pair, and then they pool all of these public keys to create one shared public key. Now, the secret key corresponding to this public key is not owned by anybody. It's not seen by Microsoft, it's not seen by any hospital. You need all hospitals to participate in a distributed decryption process to decrypt any ciphertext encrypted under this public key. So you get the benefit of having the encrypted data look like it's owned by one person, but in fact it requires authorization from all participants to view the results. So once they have this shared public key, they can all encrypt their data and send it to some central server. The central server then computes the result, and then they all use their piece of the shared secret key to run this distributed decryption process. So we have a short demo. The goal of this demo is to determine the disease prevalence by protected class. So we have a matrix that is C rows and D columns representing C classes and D diseases. And so each hospital will submit a matrix encrypted in row major order, where each entry of the matrix will represent how many people visited the hospital who fell into this particular class and had this particular disease. So, yeah, I guess, yeah, I'll have to switch laptops.
Yeah, while we switch the laptops, we can talk about how exactly this computation works. The simplest mental model for this client being the hospitals and the central server work division is as a restricted map reduce, if you're familiar. So basically, all the hospitals compute their local histograms, and that's a map operation we want people to do. And in this case, we want to see, for instance, admissions rates by race, and that you can compute that every day for every doctor. And you compute a histogram over a period of time for each hospital. From the local perspective, if you have an admission rate of 0.2 of African American patients, you don't really know if that's really out of the ordinary until you have aggregated all the statistics together. So the idea is that the reduce step is done homomorphically in the server. So as a programming model, this is incredibly simple, and all we need to do are linear aggregations. In this demo, we're not implementing division because we're just aggregating counts, so you can, so the results could be seen as an aggregated histogram.
Yeah, sorry for the delay with that. Okay, this demo proceeds exactly as we've described. The key generation functions are still dummy functions. We didn't implement this in Seal because we haven't been. Yeah, it would take a bit more time than we had, but the idea is still there. So what happens first is the clients each generate their own public-private key pairs, and then they send all of the public keys to the server, who then combines them to create this one shared public key. The server then returns the shared key to the clients, and the computation can then proceed. So the clients can then load their input data and then encrypt them with their shared public key, and then submit them to the server. And then the server can just take this and compute the result. And as you can see, because we're just doing sums, this result is very, very simple to compute. It really just uses this batched addition operation that is super fast. Yeah. The addition isn't Seal. Yeah. Okay. So then, once the clients receive the encrypted results, they all have the same result ciphertext, and then they begin this distributed decryption protocol. So then they create these decryption shares, which are posted to the server, and yeah, the result is computed and correct. Great.
Yeah, there's not much room for error because all we're doing here are addition. If we're also adding the division, there will be a little bit. But all in all, we're not really approximating any nonlinear functions, and it's incredibly powerful on what we could do, such as uncovering fairness bias and discovering the underlying causes of things that are buried in noise and biased local data, if that makes sense. Happy to talk about the details.
Okay, so finally I'm going to talk about the benefits. So first of all, we enable data sharing at a previously unseen scale. So we allow all these hospitals to be able to share their data, and this is something that hasn't happened yet, which will allow for accurate and generalizable results. So there is no requirement for us to have cryptographers present at the hospitals doing this stuff. We only require one statistician and one doctor to complete once the initial stuff has been done. The results are interpretable. We don't just have a prediction or a classification. We have some sort of comparison between different results. The key exchange process is simple compared to other schemes, and the uploaded data is encrypted and not shareable, so hospitals can upload anytime. As long as hospitals keep their keys, a centralized party can continue developing algorithms to compute statistics once everything has been centralized. Cool. Thank you very much.
Well, so if you want to do addition, you don't really need HE, right? Like, actually, you can do something much simpler to do a secure MPC kind of summation.
That's true. So what we did initially was just addition, but you could easily extend this to support more complicated operations that other, like for example, Palier could not support. In addition, the batched addition is super fast and very scalable for large tabular data sets of the kind that we expect to operate over. Yeah.
Did you think about the incentives for hospitals to participate and to answer correctly, or any other mitigations you could put in place to assure correctness in the results that are being input?
Oh, yeah.
Yeah, so we did think about that for quite a while. So I think the approach we kind of went for was that it would be beneficial for hospitals because the things which we can do with this data, they could use this for research, for finding out more information about their patients. And we also considered taking a regulatory approach. So for example, I'm afraid I don't recall the names right now, but there are some government agencies, and their jobs are to basically improve healthcare provision for disadvantaged people and people who from minority classes. And so potentially there could be some kind of legal or regulatory aspect to encouraging or forcing hospitals to participate.
Yeah, it's also worth noting that we don't have to do this for just oversight data. We could do this for much more relevant computations for medical research. One example that we gave was detecting new outbreaks of diseases or just shifts in which classes of people are affected by different diseases, maybe even uncovering patterns of how diseases develop. So I mean, it's not, this computation can really, these techniques can really be used for any computation that would benefit from more data. Yeah.
I think if there's only one malicious hospital who submit a random value, then I think this only malicious hospital will receive a correct result, but all other hospitals will receive random values. So I think there's some protection about this malicious decryption. And the other question is it possible to let some new hospital join this protocol during the computation?
I think you have to remake the keys, but that's the only thing. So in the whole schema we're talking about, including continuing to compute on the data, it doesn't actually require the clients to rehash their keys. So the idea is that if a hospital decides to withdraw, then all it needs to do is to destroy its own key, and then all the resulting computations wouldn't be available for anyone. And then we kind of restart this round with new participating members, if that makes sense.